Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 8 of our electrical machines chapter. So we are discussing about transformers. So today we will mainly discuss about more about dot convention in multi-window transformers, okay? And about referring of circuit elements, and we will do a few questions and we will solve all those. Okay, so let's start. Basically, dot convention we have already discussed in the previous lecture. Okay, now I will discuss about referring. How can I refer? Like if I have a impedance connected on the coil 2 winding 2 of this transformer, what is the impedance that I can see from this uh, winding 1? Okay, if I have connected impedance Z and theta Z, so I know one relation that will be valid according to Ohm's law, that V2 by I2 will be equals to the impedance, that is Z angle theta Z. Okay, this has to follow. Okay, and I know that transformer we have already derived that currently it is ideal transformer. So if it is ideal transformer, so I know the induced EMF and the applied EMF both are same. So V2 by V1 will be equals to N2 by N1, and also I know that I1 by I2 is also equals to N2 by N1, or let's write it otherwise, I2 by I1 equals to N1 by N2. Okay, I2 by I1 is equals to N1 by N2. Okay, so what I can do is I can divide these two, right? Like if like these two are equal, correct? What I can do, I can divide these two. If I divide these two equations, like this is equation 1 and this is equation 2, so what will happen here? It will be V2 by I2 into V1 by I1 equals to this will be N2 by N1 whole square. Okay, so I know my V2 by I2 is what? V2 by I2 is Z, right? And what is V1 by I1? V1 by I1 will be the impedance seen from this point. V1 by I1 will be the impedance seen from this point. Okay, this is what my V1 by I1 will be. So I can say that I can say that my V1 by I1, that is the impedance seen from the winding 1, or I can say the referred impedance of Z secondary winding, right? Z dash will be equals to what? This will be V2 by I2 into N1 by N2 whole square. So what is V2 by I2? V2 by I2 is this, right? So it is Z theta Z and a term that is getting multiplied, that is N1 by N2 whole square. Okay, so very important relationship, that if I have any impedance on the other side of a winding, and if I want to see that impedance here, right, measure the impedance here, what will be the impedance that will be seen from the other winding? So basically what you need to do is you need to multiply the turns of that winding whole square. Sorry, you have to multiply the turns of that winding in which you want to refer to, divided by the number of turns in the previous winding in which the impedance is actually present, and square it. That's it, and multiply with the impedance value. So it will not change the phase, so phase won't be affected. Okay, very important, as transformer is a linear device, it will not affect the phase. Okay, so phase won't be affected, only the magnitude will be changed. That's it. Okay, so this, like, why do we do this? So basically ultimately what is happening is, let's say if I am applying a AC source at the primary, so the whole circuit, right, whole this circuit can be changed to simply a equivalent impedance, that is Z like N1 by N2 whole square into Z theta Z. So my circuit analysis point of view will be very easier. Okay, so that is why we do this referring business, right, to make our circuit analysis very easier. So this is known as the referred impedance. Sometimes it is called as referred impedance on the winding that I want to measure the current or something. Okay, so analyzing this will be very hectic, right? So either what you can do, if let's say you wanted to find out this I1 current, there are two ways to find out this I1 current. First, you have applied a V1 voltage. From there you find out V2, because V2 by V1 is N2 by N1, and from there you will be able to find out I2, because I know Z, so V2 by Z will give me I2. Now you put this I2 in this equation, okay, and from here you will find out I1. This you can do, or you can directly take this impedance, can refer it to the primary, and then directly solve the circuit. From here you can directly find out the value of I1. So I1 will be equals to V1 divided by the impedance value, whatever is the impedance value, that is N1 divided by N2 whole square Z into theta Z. That's it. Okay, so that's what you need to do. Got it? Very simple, right? So just one thing you have to keep in mind. So impedance, right? Impedance is getting multiplied by N1 by N2 whole square. So if I have a, let's say if my impedance is a resistor simply, so the referred resistance, right, Z dash will be what? It will be N1 by N2, or R dash, I can say referred resistance will be N1 by N2 whole square into R. What about, like, this was the point 1. Point 2 is, if my impedance is a inductance, that is j omega L, so my referred inductance will be this, I can write here, or R dash or referred, whatever you want to write. This will be N1 divided by N2 whole square into L. Now if my impedance is a capacitance, right, so Z is equals to 1 by j omega C. So my referred capacitance, will it be N1 by N2 whole square into C? No, this is incorrect actually. This is not correct. Okay, this is not correct. Ultimately, right, this formula you should remember that impedance will be multiplied by this, not inductance or capacitance. Okay, impedance. So impedance here is j omega L. So here actually what happens is my Z dash is basically Z into N1 by N2 whole square. What is Z? Z is j omega L. So j omega L into N1 by N2 whole square. And also obviously if it's inductance in the referred side as well, I will get a inductance only, right? So I can equate this value N1 by N2 whole square. I can equate this value to be equals to j omega L dash. Okay, so my, from here I can directly say that my L dash will be equals to N1 by N2 whole square into L simply. That's it. Okay, so this is the actual way how you derive. So for capacitor, right, for capacitor what you will see is I have basically my referred impedance will be a equivalent capacitance only, that is j omega C dash. That will be equals to N1 divided by N2 whole square into what was the actual capacitance? It was 1 by j omega C, that is into Z only, right, into Z. So basically Z is 1 by j omega C. So that is on the secondary side. Now what will happen, this j omega will get cancelled. So my C dash actually is the inverse. C dash equals to C into N2 by N1 whole square. Okay, so it is opposite. For capacitance it is opposite. Just be careful regarding that. Okay, except that everything is fine. So now why is dot convention important? So this dot convention is also important if I want to refer any like if I want to refer any voltage source and current source as well, that we will discuss. So just wanted to quickly tell this, that impedance already you have remembered. Just how do you remember this thing? How do you remember? So how do you remember the referred impedance? So referred impedance, you remember it like this, that my referred impedance, okay, my referred impedance, just remember the impedance one, other you can derive, right? Referred impedance will be equals to the original impedance, whatever was present in the uh, previous winding, original impedance, into the number of turns where I want to refer to, into the uh, destination turns, or the place where I want to refer, the winding where I want to refer, okay, that impedance. So into the destination turns, basically number of turns in the destination winding, divided by the original turns, like where originally this impedance was present, right? Okay, so that's how you remember, basically that's how you remember this formula, and others you can easily remember. Now we will discuss how can you refer different kind of voltage sources and current sources. So voltage source also you can refer. So let's say if I have a voltage source here, this resistance can be easily referred, right? So resistance, if I want to see, like if these are the circuit elements that are connected here and I want to refer everything to the primary for my easier analysis, so the resistance can easily be referred, but what about the voltage? Okay, I know that this resistance can be easily referred here, like this resistance will come here, and what will be its value? Its value will be n1 by n2 whole square. Okay, that will be its value. So but what about the voltage? How do I bring this voltage here? Okay, that is what I want to know. How do I bring this voltage here? So very simple thing is that if this, let's assume that initially this resistor is not there. If this resistor is not there, okay, if this resistor is not there, and if I want to refer this voltage in the primary, like what will be the simple voltage equation, right? So basically my v1 by v2, that is equals to e2 only, or el only in this case, is equals to n1 by n2. So my el, or my v1 will be equals to what? V2 is el, right? So el into n1 by n2. Okay, so any voltage source will just follow this ratio. Okay, so impedances will be squared and voltage source will not be squared. So this is also the destination turns divided by the source turns, okay, into the initial value. But here I don't have any square. For impedance I had square, but for voltage sources I did not had any square. Okay, so that is how you refer voltage sources. That is how you refer any voltage source. So if you want to actually verify this, right? So whether this is correct or not, how will you verify this? So like this works for this simple circuit. I have R and EL, then how will it work? If I have R and EL, then how will it work? So if I have R and EL, then basically what I can say is, what is this current I2? So I2 will be equals to this V2 minus EL divided by R, correct? And ultimately what I have to see is, I have to see here. So what is my current I1? That is what I wanted to see. What is my just hold on, this is for the DC circuit, we are still discussing for the AC circuit. So what is my current, so I2 is this. So I know transformer has to follow this relation, that I2 by I1 will be N1 by N2, okay, and my V1 by V2 will be N1 divided by N2. Okay, so I can replace this V2 here with V1, sorry, V2 into N2 divided by N1 into V1. I can replace this V2 like this, right? Here I can replace the V2. R also I can replace. R I will not replace for now. I will not replace R for now. Okay. So I just wanted to find something. So I1, I2 also I can replace, right? I2 is equals to I1 into N1 divided by N2. Okay. I2 is equals to I1 into N1 divided by N2. So I can directly write that my what is this? V I2 is equals to I1 into N1 divided by N2. This is equals to V1. Sorry, V2 is this, right? So this is N2 divided by N1 into V1 minus EL is still there. Okay, EL is still there and R is still there. Okay, all these are like of course AC sources. So what else can I do? What else can I do? So what I can do, I can write this I1. Okay, this I1 equals to, if I take this N2 and N1 on the right hand side, so this will go on the right hand side. So this will be basically and if I divide this, if I divide by N2 by N1, if I take common N2 by N1, okay, I am taking common N2 by N1 here. So if I take common N2 by N1 and I am multiplying N2 by N1 by N2 on both N2 by N1 on both sides, so this will be N2 by N1 twice, and here I will have V1 minus EL into, I am taking common N2 by N1. So here what will come? N1 by N2. Okay, N1 by N2 divided by R. So basically I am trying to convert this circuit. You will understand. So my I1 is equals to what? This I can take in the bottom. I want to club these terms together with R. So this will be actually N1 by N2 whole square into R, and this will be V1 minus EL into N1 divided by N2. So basically what is this? Like if I convert this into circuit, right? If I convert this into a circuit, this means basically I have a voltage source here, V1. I have a resistor that is connected between this source whose value is EL into N1 divided by N2, and this resistor is there, right, whose value is N1 divided by N2 whole square. Like if you convert this equation, so I2 current is coming here, right? I2 current is coming here. So if you convert this equation, right, into a circuit, it will behave something like this. Isn't that what we derived earlier? So I did not actually discuss there. So I told you, right, the voltage source will be what? The voltage will be scaled by N1 by N2. The resistor will be scaled by N1 by N2 whole square. Exactly that is happening, right? I proved to you. I proved to you that the resistance has been scaled by N1 by N2 whole square and voltage has been scaled by N1 by N2. So the scaling factor for voltage and resistance is almost same. Just here the square will not be there. Square will not be there. Okay. Now what if I have a DC source? Can I refer DC source as well? So actually I cannot refer DC source. Okay, I cannot refer DC source. So currently I have no, if nothing is mentioned, you will always assume the transformer to be ideal. So all the ideal properties will be valid. So if it is ideal transformer, that means if I have applied a DC voltage here, there is no change in voltage. If there is no change in voltage, there will not be any change in flux. There will be a constant current that will flow through here, right? This winding will just act as a short circuit because this is just an inductor, and we know whenever we have an inductor, initially there is some transient. After that what happens? Simply the inductor becomes short circuit at steady state, right? So a constant current flows. What is the constant current? Constant current is simply EL by R. So due to this constant current, there will be a constant flux. There will be a constant flux of EL by R. Okay, there will be a constant flux. So flux is this, right? Constant flux will be there. So flux is constant. So it is not time varying. It is not time varying. So if it is not time varying, that means basically what will happen? That basically means that there will not be any induced EMF here. So here V is equals to N d phi by dt, no induced EMF because flux is constant. If flux is constant, voltage induced will be 0. So we cannot refer DC voltage source. So important point is DC voltage source cannot be referred. DC voltage source okay, DC voltage source cannot be referred. What about current source? So remember, one more thing you remember, that these, right, these dots are here. Remember to place the dots together. So whenever I am connecting this circuit here, okay, remember to place the dots together. So this will be very, very handy once we will come to those positions. So but remember, whenever I am referring this to the primary, right, make sure to connect the dots, very important. So make sure to connect the dots. Basically dot should connect to dot. So this point of the wire should connect to the dot, right, because dot should connect to dot and the non-dot should connect to the non-dot. Very important. We will do few examples, we will see this, don't worry. Okay, so here as well, if I have a current source, like series resistor actually does not matter anyway with a current source, but if I want to refer a current source, so same proof if you do for current source, it will be just the opposite. So I know why it will be opposite, because I2 by I1 is simply equals to N1 by N2. So my I1 current will be equals to what? I1 current will be N2 into N1 divided by I2. So it will be just opposite of the voltage. It will be just opposite of the voltage. So my equivalent circuit, make sure to remember the dot will connect to dot. So equivalent of this circuit will be, here I will have a voltage source. Here I will have a voltage source V1. Okay. Then remember this dot will connect to this dot. Okay, this dot will connect to this dot here. Although the resistor does not matter in series, because resistor in series with the current source is redundant. So this will be N this will be actually resistor will be the where I am referring N1 by N2 whole square, and this is the dot of the secondary coil, right? So now a current source will be there. This is a AC current source. Okay, so IL will be scaled by the opposite factor basically. So it will be N2 by N1. So its own turns divided by the turns where I am referring to. Okay, so this is what my IL will be equals to. This is what my IL will be equals to. Okay, so that was about it basically. So yeah, now like this is the one question that you can do to understand how actually basically we have to refer, right? Now you just don't simply connect this one here, because remember the dots are different. So please pause the video, try to solve this by yourself. Okay, try to draw the equivalent circuit, refer to the primary side. Okay, this is the primary side, try to refer. Okay, so we will do it basically. So I will copy this circuit. The circuit will be exactly ditto copied. Okay, and it will be connected here. Okay, if I'm just referring, and if you have done it, so me shouting for 30 minutes, if you have done something like this, right, me shouting for 30 minutes was just a waste. Okay, because I told you that please connect the dots with the dot, don't connect this one with here. Okay, make sure they are in the same polarity. So this is dot, so dot must come here. Okay, dot should be coming to the dot. So actually this will be flipped basically. So basically this will be flipped. So this point will not come here. Basically I will have a resistor. So this dot is here, right? So this dot will go here. So in the top one I will not have anything. I will not have anything. In the bottom I will have everything. So here I will have a R. Okay, this resistor, which will be scaled of course to the primary. So it will be N1 divided by N2 whole square. Then I have a voltage source. Okay, and just see where is the dot connected. So dot is connected here actually with this dot, so it should be at the top only. That is fine, it should be at the top only. So this voltage will again be scaled with a factor of n1 by n2, n1 by n2, and then I have a capacitor. So by what factor capacitor gets scaled? Capacitors get scaled by opposite factor, right? It gets scaled by opposite factor of the resistor actually, right? So it will be n2 by n1 whole square. Now I have a current source. So current source again will be scaled by the opposite factor of the voltage source. So remember, where is the dot? Dot is here. Okay, dot is connected to the non-dot here actually. So it will be something like this. Okay, remember dot is here. Just be careful of the dots. That's why we gave so much time to the dot polarity, right? Basically dot tells me the instantaneous polarity at a particular instant. Okay, if this point is high, then this point will be high, something like that. It talks about the instantaneous polarity. So this will be IL, and of course scaling factor will be n2 by n1. Okay, n2 by n, that's it basically. So yeah, that's it basically. That's it basically. So that's how you will scale basically. So yeah, we are done. We are done with this. Have I done? Okay, 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 okay. One more mistake. Sorry. Capacitor will be coming at the bottom, right? I am making my own mistake. I scolded you guys and I'm making the own mistake. So capacitor will of course be coming here because it is connected with a non-dot, right? So it will come in the bottom actually. Sorry, my fault. So it will come here. Okay, and this current is connected with the non-dot. Sorry. This, hold on a second. This will be at the bottom only. This capacitor, yeah, this capacitor will come at the bottom. That's it. Capacitor will come here. That's it. Rest everything is correct only. Okay. So yeah, I hope you have understood this question. So that's how you refer basically. Okay, that's how you refer. So yeah, now let's come to few questions basically. So I'm asking you, which of the circuits are invalid here? Okay, which of the following circuits are invalid? If you see, sometimes I have applied a short circuit here, sometimes it is open circuit, sometimes I'm applying two voltage sources, sometimes I'm applying like some different amplitude, sometimes there is a what is that question, phase difference, right? So just pause the video and tell me which of the circuits here actually are invalid. Okay, whatever knowledge we have gained till now, try to implement that logic. So let's start slowly. Let's start with the circuit A. So if I see in the circuit A that the secondary is short circuited, that means the voltage across the secondary is 0 and primary has voltage V1. Is it possible? Remember, nothing is mentioned, so we will assume ideal transformer. Okay, ideal transformer. If I assume ideal transformer, that means that secondary is shorted and primary is V1. So is it possible? Because transformer, it has to produce flux. If it is producing flux, then that MMF balance equation needs to satisfy. That means V1 by V2 must be equals to N1 by N2. But here it is not correct, right? So basically what will happen, coil will burn. So circuit A is invalid. Okay, circuit B. So I am applying two voltage sources, one at the primary, one at the secondary. So if I find out the ratio of the induced voltages, right, for circuit B, if I find out the ratio of the induced voltage, E2 upon E1 must be equals to N2 upon N1. So N2 upon N1 actually they have given me as 1 by 3 or N1 by N2 is 3. So N2 upon E2 by E1 is N2 by N1. But here, right, E2 is what? E2 is 2V1 and E1 is V1. So it is basically 2V1 by V1. So it is coming out to be 2 here. It is coming out to be 2 here, but actually N2 by N1 is 1 by 3, which is of course not equal. Both of them are not equal. So again, this circuit is again invalid. What about C? Let's check for C. So in C, I am observing, yes, it is correct that E1 by E2 or E2 by E1 is coming out to be N2 by N1. Okay, it is coming out to be N2 by N1. That is what? That is, actually I made a mistake here. My bad. Actually, it should have been, okay, I made a mistake. This should have been actually 3 here. My bad. This should have been 3 and this should have been 1 only. So if I, sorry for that. So now, if I see the ratio, right, that you will say, sir, yeah, N2 by N1 is 1 by 3 and E1 is basically, E1 is what? E1 is 3V1, E2 is V1. So you will say E1 is 3V1, E2 is V1. So it is coming out to be 1 by 3, sir. Then it is correct. It is a valid circuit. I will say no, it is not valid circuit. Why it is not valid circuit? Because in transformer, right, the phase does not change. Here, right, the phase is changing actually. So we transform the voltage by a constant multiple that does not have a phase. That is, that has a 0 degree phase or 180 degree phase. At max, it can have 180 degree phase or 0 degree. Okay, so we multiply by a constant number that has no phase. Okay, no phase difference. So if I multiply this constant number, real number, no phase, but here it is showing that I have a phase difference of 60 degrees. How did this phase difference came? If this is a ideal transformer. In case of practical transformer, it is a possibility that there will be a phase difference. There will be a possibility. I will discuss about that. But for ideal transformer, no possibility. Okay, so phase difference is not possible. So this is also invalid circuit. So A, B, C, all of them are invalid circuit. Now let's discuss about D. Okay, so if I discuss about D, so in D, is it a valid circuit? So this is actually a valid circuit. Why is this valid circuit? So if I just take this circuit, so for you to understand why is this a valid circuit, you should understand this thing, that a voltage source allows any amount of current, but the voltage is fixed. A current source allows any amount of voltage across it, but the current is fixed. Okay, so the secondary coil, this source is telling me that the current across the secondary coil I2 will be 2V1. Okay, so what will be my I1 current? I1 current will be what? It will be just like I1 by I2 will be N2 by N1, correct? N2 by N1. Okay, I1 by I2 current is N2 by N1. So it is N2 by N1. So N2 N1 by N2 is 3. So N2 by N1 will be 1 by 3. Okay, so I1 current will be basically 1/3 of this. Am I correct? Yes. So it will be I2 by 3. I2 is 2V1 by 3. So I1 current, right? Current across this voltage source is 2V1 by 3. Will this voltage source allow this current? Yes. This is an ideal voltage source and it will allow any amount of current. So no problem. What about the other portion? What about this portion? So now this supply is telling me that the voltage of the primary winding is fixed, that is V1. So what will be the voltage across the secondary winding? That is V2. V2 will be what? N1 by N2, and N1 by N2 is 3. N1 by N2 is 3. So this will be equals to basically V2 by V1, right? V2 by V1, N1 by N2. So yeah, N2 by N1. So my V2 will be N2 by N1, that is V1 by 3. V1 by 3. Now will this current source actually allow a voltage of V1 by 3 across it? Of course, it is an ideal current source. It can allow any amount of voltage. So no problem. No condition is getting violated. All the conditions are satisfying of the transformer and circuit is also fine. Okay, so this circuit is not invalid. This circuit is a valid circuit. All the others are actually invalid. So if you will see same reasoning, this circuit E also will be invalid because the ratios will not match basically, because this is telling me primary current is fixed, this is telling me secondary current is fixed. If secondary and primary currents are fixed, that means their turns ratio must match, but here it is like ratio is 2, here it is 3. Of course it will not match. So circuit E is also invalid. Okay, so E is also invalid. What about F? Sorry, this will be F. What about F? So F again is invalid. Why is F invalid? F is invalid because Again, the currents actually are fixed, right? Just like this circuit A, voltages were fixed here, and this is invalid circuit. Same here, my primary is telling me that current is fixed V1. So what should be the current of the secondary? It should be N1 by N2 into V1. But current here is getting fixed to 0 amperes. Of course, not possible. So this circuit is again invalid circuit. Okay, invalid circuit, because this will not work as a transformer. So basically, what will happen? Uh, this current source is there, right? Some current will flow through the winding that can damage the winding. That's it. Okay. So yeah, that is again, this will not work as a transformer. This will not work as a transformer. Simply a AC, like it is simply a current source with a, by invalid I mean which will not work as a transformer. Okay, that is what I mean. Current source with a simple j omega L, whatever the impedance will be, but doesn't matter. Whatever there is, current source will always supply the current whatever it wants to, right? Because it does not matter whatever impedance reactance is there in series with the current source. Okay, so yeah, now this was about the this referring and about the validity of a circuit, validity of a transformer. Invalid as a transformer, I should write here invalid as a transformer, as a transformer. Okay, so yeah, now let's discuss a bit about multi-winding transformer. Okay, so we were like solving for the dot polarity, right, for a single window transformer. Now if I have multi window means like I have a window, this is like a window, right? This is one of the window, this is one of the window, like 3 legs I have of this code. So here if you just go by your method, right, that if I have a dot here, that means this will be dot here, and it will be dot here. It will actually be wrong. It will be actually wrong. Why will it be wrong? So let me not just do it here. Let me just copy this thing and do it in the next page basically. So if I go by my method, whatever we have discussed, that I have a dot here, I have a dot here. Okay, but is it actually, let's solve by fundamentals, let's solve by basics. So if I solve by basics, that I have a dot here, that means I'm applying some voltage here, right? Some E1 voltage here. So if I apply some E1 voltage here, assumption is current will flow like this. If current flows like this, okay, then it induces a flux, correct? It induces a flux. So flux is like this. So this will be here, and this is my flux. Okay, and of course I have a flux here as well. Okay, so yeah, so yeah, I have a flux here as well, right? This is my flux, like this flux will flow like this and like this. These will be the directions of flux, right? Because they will form a closed loop. Flux always forms a closed loop. Okay, so these are the direction of the flux. So I know if flux direction is this, I have to somehow induce a voltage, like some voltage will be induced here, such a way that it will oppose, right? So of course, again the old method, we connect a resistor here, and let's assume a polarity. Let's assume this as plus minus. So this is plus minus, right? So current will flow like this. If current flows like this, that means it is flowing like this. Okay, it is flowing like this. So now if I apply the right hand rule, so I am seeing that I am actually aiding the flux direction. So this current is actually aiding the flux direction. So of course this is wrong. So whatever I had assumed, this is wrong. So this will be plus and this will be minus. Okay, so this will be, my currents will flow like this. Okay, so now if I curl my fingers, I see I am going in the up direction. That means I am opposing the initial flux. So this is correct. So this is plus. So this will be dot actually. this will be dot here. And what about this one? So again here, if I connect R, again if I do this, right, plus minus, so this will be again, this will be like this, so again it will aid actually, so this is wrong, this is wrong, this will aid the initial flux, no. So I will have a plus minus here. Now current will flow like this, so current is flowing like this. Okay, so again now what I am doing, I am opposing the initial flux. Okay, I am opposing the initial flux, so whatever I had assumed is correct. So dot will be here. So what we had used our initial technique, so our initial technique is working here, no problem, because dot is here in front of the core, here also dot is there in front of the core, here also dot is there in front of the core. What about the other circuit? What about the other circuit? So other circuit things will be a bit different. Okay, so I will copy the other circuit as well. I'll copy the other circuit as well. So if I copy the other circuit as well, so here I have a dot. Okay, and of course the same procedure whatever we will follow. So initially this is plus minus, right, this is dot, so current will flow something like this, correct, current flow something like this. So what is the flux direction? So if I curl my fingers, flux is going downwards. Okay, so flux is going downwards, so flux direction will be somewhat like this. Flux is going downwards. So no, not like this, it will be, sorry, it will be going like this. Okay, here it will go downwards, here it will go upwards, here it will come back, here it will come back like this, right? So it will be like, it will start from here, then go here, come back, it will start from here, then go here, then come back. Okay, that's it. So these are the direction of the flux, these are the direction of the flux. Okay, so now important fact is what will be the polarities here and here. Okay, so again same basic method, if I connect a resistor here, then of course I need to oppose this initial flux. So what should be the direction? Direction should be like, current should be like this, so that I'm going downwards, flux should be downwards, so current should be like this, right? So if it is like this, that means it will, current direction will be this. Okay, then only I will oppose the initial flux. So if current is like this, that means current is flowing here, so it is plus minus here, so dot will be actually here. And for this again I need to oppose the initial flux, here the flux is going upwards, again I need to bring it downwards, so again current direction will be something like this, so it will be this. I need to oppose the initial flux, so current direction should be something like this, so that I can make the flux downwards. Currently the flux is upwards, so again if I connect the resistor, so I will have a plus minus here, current is flowing like this in the resistor, so plus minus here, so I will have a dot here. So if you see, if I go by my previous method, right, so if dot is in front of the core, in front, if the dot is, sorry, if the coil in front of the core has a dot, then all the other coils also should follow the same. Actually it's not following. So in this third coil, right, actually the dot is behind the core. If you see in the third coil, dot is behind the core, so it's a problem. So basic summary is, don't apply the dot trick in multi-window transformer. So this, right, I have not taught to EC guys, because of course they will be they will go berserk, right, like they will say, sir क्या पढ़ा रहे हो, इतना क्या पढ़ा रहे हो, पागल करवा दोगे ट्रांसफार्मर से, मतलब, तो that is the main thing, right? So of course they don't need this much amount of knowledge, that's why I told them that use their method and you will be done. Okay, so in their exam also that method will come and they will be done, but for us we are electrical guys, right, so we need to study more comprehensively. So of course I am telling you all the edge cases where the method will not work, so it is very important to know where the method will work and where the method will not work. Okay, so let's solve few questions. So I will like show you few questions, try to solve by yourself, and after that I will come back with the solutions. So these are the questions basically. So these are the questions, this is one of the questions, This is the other question, and this is question. There are a lot of questions. This is another question. So these are all good questions actually. Try it out by yourself, and I will come back with the solutions. So you can take a pause and try to solve all the questions. So let's start with this question. So we have this question where we have to find out the input impedance seen from here. Okay, what will be the input impedance seen from here? Remember, I cannot just simply bring this 5 ohms here because I have mutual coupling as well. Okay, and the inductance values are also given. So we have to go by the basic approach. What is the basic approach? So basic approach will be, I will just copy the transformer. Okay, and I will just write the I will apply the Mace law. So Mace law will apply. So this will be some I2 current, I2 of S. Okay, I'm converting everything in terms of S because they have asked, if you see, in S domain only. So this will be I1 of S. Okay, and this is my basically V input of S, right? So my input impedance Z in of S will be equals to V input of S divided by, just hold on, yeah, V input of S divided by I1 of S. Okay, so now let's apply the mesh law. So if I apply a KVL in this loop, first loop, so it will be minus of V in minus of V in S plus 4 I1 of S plus, remember, so this is the drop across the inductor. So inductor is what? Inductor is j omega L. So it will be j omega. Omega is omega, not M, L, sorry. J omega is S, right? Sorry, it will be SL, right? It will be SL. So it will be 6 into S, 6S. Also there is mutual inductance as well. So if I convert the mutual inductance, it will be S into 1. Okay. So drop in the inductance is 6S, that is the reactance, into the current, obviously I1 of S. Okay, this is the drop basically. Now of course the mutual inductance will oppose the cause. Let me just find out the current. So here current is entering the dot and here current is leaving the dot. Okay, so here current is entering the dot and here current is leaving the dot. So if we remember, then what would have happened? Then the voltage would have simply opposed, right? If in the one of the coils current is entering and in the other coil current is leaving, that means the mutual voltage will oppose its initial cause. Oppose its initial cause. That is, if I have a plus sign over here, the drop will be with minus sign multiplied by the mutual inductance S into the, of course, the current in the secondary coil, because this is the reason for which a mutual voltage will be developed, current in the other coil. All these I have discussed very well in the chapter 0. So that's why basics is very, very important. Of course, I will show you using other method as well. I will show you using the other method. Okay, but I don't want you to use that method because conceptually you don't understand it. So here S into I2 will be equals to 0. From here, also this is the first KVL, right? What about the next KVL? This is the next KVL, okay, in the loop 2. So in the loop 2, again the drop will be like this, plus minus, drop will be plus minus S into 4 into I2 of S. Again, both mutual voltage will oppose each other. So if this is plus, then the other one will be simply minus. Okay, so this will be minus, again the mutual impedance into the current in the other coil. So it is I1 of S. Now again the current flows in this direction, so drop across the resistor will be like this. Okay, so it will be plus 5 into I2 of S, that is equals to 0. Okay, so I can directly write here I2 of S into 4S plus 5 equals to S into I1 of S. So my I2 of S will be equals to S into I1 of S divided by 4S plus 5. Okay, now I will replace this in the first equation, in the equation 1. I will replace I2 of S in the first equation. So it will actually become, if I copy this, so my basically V of S will be equals to this value. Okay, I2 of S is S into I1 of S divided by 4S plus 5. So I can directly say that my V of S over I of S will be equals to 4 plus this will be, now what are the options actually? If I see options, right, it is written like with a common denominator 4s plus 5. So I will bring everything into like common denominator. So this will be 4 into 4s plus 5 plus 6s into 4s plus 5 minus s square divided by 4s plus 5. So this value will be 24s plus 20 plus 24s square plus 30s. Am I doing anything wrong here? I'm just trying to check, because yeah, no, it is it is fine, I guess. Okay, this will be 4, 6 is there. Okay, minus s square, so this is 23s square is there. Okay, 23s square is there. 46s is actually not there. Where am I doing it wrong? 46s is not there. 24, 30s, 20, sorry, this will be 16s, right? This will be 16s. So minus s square divided by 4s plus 5. So the value comes out to be like this. It will be 23 s square plus 46 s plus 20 divided by 4s plus 5. Okay, so 23 square plus 46 plus 20 divided by 4s plus 5 is present in the option A. Now you could have done it in a different way as well. What you could have done is simply write like there is other way, other teachers will solve like this. I have to also explain like this as well, that if I have this circuit, right, you can convert this equivalent circuit. I understand that first you have to assume few currents. So if my currents are like this, I1 and I2, that means in one of the dot current is entering, in the other dot current is leaving. So I can directly write here I can directly write here that I can convert this circuit into equivalent. So this will be 4 ohm. This will be like inductance will be converted into the Laplace domain 6s, and basically the mutual inductance is denoted with a voltage source, dependent voltage source on the other side current. So it will be like, what is the mutual inductance value? That is S into the current in the other side, I2. Okay, now why this plus minus? Because it will oppose its initial clause, that's why it is plus minus. Okay, that's why it is plus minus. And here as well the same thing. This kind of question we have already done, not exactly in the chapter 1, but we have done something like this. So this is 4s and this will be my 5 ohm. So again the direction of the current is somewhat like this. So here what will happen, like, that's why there is a bit of confusion, right? Because this also will be plus minus only. So as there is a confusion always, I don't tend to use this like method. But what you can understand, like, what is the voltage direction here? It is plus minus, right? This will be the voltage drop direction. So it will be in phase opposition. So if I have a plus here, then I will have a plus here and minus in the other side. Same here, right? What will be the direction of the drop? Direction of the drop is like this, plus minus. So if I have a plus here, then again, like if I have minus here, I will have a plus here, and if I have a plus here, I will have a minus here. So basically, right, it will be just in the opposing direction, what I meant to say. Yeah, sorry, like this will be minus plus. I know there is a confusion, that's why I don't use this actually. This will be minus plus because this will oppose, I mean, if I write the voltages, right, it will be basically, if I write the voltage in this particular section, it will be VL1 minus SI2, and here also same thing, right? It will be like both will oppose each other basically. So there is a confusion, and trust me, in most of the books they will never explain this. Okay, even the signs are wrong in most of the books. Okay, I just recently saw a book, their sign was wrong. Okay, so that's why we solve with basics. We know what is happening in the circuit, and like, of course, this is there, right? This is already there. Okay, so yeah, that was it basically. So now let's solve another question. So we have this question: an ideal transformer has primary winding with 200 turns. On the secondary side, the number of turns between the points A and B is 600. Okay, this many has 600 turns, and between, okay, this will not be okay, this will be 2000 only. Sorry, this was supposed to be 2000 voltage. This was supposed to be 2000 voltage. Sorry. A and B 600, and B and C it is 400, and between A and C it is total 1000. Okay, resistor is connected between A and C, that is, that consumes 10 kilowatt of power. Additionally, a load is connected between A and B that consumes that has okay, that has impedance of 2000 angle 45 is connected between A and B. Given the primary voltage is 2 kilovolts, determine the primary current. What will be the primary current? So there are many ways to solve this. Either you refer everything to the left hand side, but it will be a bit difficult. You can still refer it. You can still refer everything to the primary, or you can directly find out the current here, secondary current, and you refer the secondary current. Both ways work. Both ways work. So we have to find out the current in the let's find out the current in the secondary. So how do I find out the current in the secondary? So this is my secondary current, IS. Okay, so what is my IS equals to? So my IS will be equals to IL1 plus this current, right? Let's assume this current as IAB for now. IAB for now. Okay, let's assume this current for IAB for now. So this will be IAB. This is my IS current. So what is IL1 current? So IL1 current, right, will be the voltage VAC divided by the uh, like resistance, but resistance they have not given me. It has just told me that it consumes 10 kilowatt of power. So if it consumes 10 kilowatt of power, then I can directly say that power in the resistance will be 10 kilowatt. I can write this as either IL1 RMS whole square into R, or I can directly write this as PR will be V AC whole square divided by R. Both these work. Okay, both of them work actually. So yeah, so now we can, do we know VAC? Yes, we know, right? I know my primary voltage, that is 2 kilovolt. So my secondary voltage VAC, secondary, how many turns I have? 1000. So it will be like same flux is flowing, right? So of course the ratio will be according to the turns ratio. So 1000 divided by 200. So primary has 200 number of turns. So VAC will be 10 kilovolt. So VAC is 10 kilovolt. So this will be 10 kilovolt whole square divided by R. So basically I just wanted to find out the current, right? So from here I can directly say it is 10 kilowatt. So I can write it here that this will be 10 into 10 raised to power 6 divided by R equals to 10 into 10 cube. So R, I can get the value of R. This will be 1 kilo ohm. Now what will be the value of the current? Because mainly I am interested in the current. So current will be, like, you can find out anywhere. It will be either VAC IL1 will be equals to VAC divided by the resistance 1 kilo ohm. So VAC is 10 kilovolts, so it will be 10 ohms basically. Sorry, not 10 ohms, 10 amperes. So this is the RMS value. Remember, these are not DC values, these are all RMS values of the current. Okay. Now, is there any phasor involved? No. This is a purely resistive circuit, so it will be 10 angle 0. Remember, it will be 10 angle 0. Okay, that will be the value of current IL1. Now, how do I find out the current IAB? Okay, IAB will be what? IAB will be simply the voltage VAB divided by the impedance. So IAB will be the voltage VAB divided by the impedance. ZAB. So what is the voltage? Again, right? Same flux is flowing throughout. Same flux is flowing throughout the whole of this impedance, whole of this coil. So again, the turns ratio will be 600 by 200 now. So VAV by V primary, that is 2 kilovolt, will be 600 divided by 200. So VAV will be equals to 6 kilovolt. Okay, so it will be 6 into 10 cube divided by ZAB. ZAB is basically 2000 angle 45. So from here it will be 3 angle minus 45. That sorry, this is my IAB. Okay, so my IAB is 3 angle of minus 45. Now I can simply add the two numbers. I can simply add the two numbers and I will get my result. Okay, so my I secondary, right, or my I2, whatever I have written here, I secondary or IS, it will be equals to what? It will be IL1 plus IAB. IL1 was 10 angle 0. Remember, these are phasor quantities, you cannot simply add them algebraically. Minus 45. So this will be equals to so this is 10 3 by root 2 minus j 3 by root 2. So this will be equals to 3 divided by root 2 plus 10. So this is 12.5 12.1 minus J 2.121. So if I just calculate the overall values, 2.121, so it will be 12.30. Angle will be 2.121 divided by 12.121 tan inverse. So angle will be simply almost 10 degrees, minus 10 degrees. This will be the secondary current. What will be the primary current? Primary current will be just refer, right? So I primary upon I secondary will be the opposite of the turns ratio. So it will be N2 by N1. So it will be 1000 divided by 200. So my IP will be equals to 5 into IS. So 5 into IS, 12.3 into IS, that is 61.5 angle minus 10. This will be the answer. Okay. Now if let's say we would have wanted to solve it some differently, what we could have done, we could have directly referred this to the primary. Okay. So this was the method 1. Let's go into the method 2. Okay. So this will be my voltage source here, and I will have this is there. And now how will I refer? So I will refer this impedance according to its turn ratio, right? So this impedance is 2000 angle 45. So if I want to refer to the primary, I have to write the primary turns divided by the turns in this particular winding, that is 600 whole squared. So it will be impedance here, and actually they should have provided dot. If they like that, if some dot is here, the same dot will be here, right? Because winding orientation is provided. So this will be 200 divided by 600 whole square into the impedance, that is ZAB. Okay. Now what about this? I told you, right? If you are referring power actually does not get referred, right? Power whatever is, it remains constant. Power remains constant in the secondary. If some resistor is consuming 10 kilowatt on the secondary, same resistor will consume the same 10 kilowatt in the primary. This I have proved to you in the first lecture. V1 into I1 is equals to V2 into I2. Okay. So as current gets scaled by the inverse factor of the voltage, so that's why the cancellation happens. So here I will have the resistance value will be still R, but I know this resistance will consume 10 kilowatt of power. Okay, and here I have 2 kilovolt of voltage. Now it is so simple, right? Now can I solve it again? So I have to find out this current. So how do I find out the current? So what is the current through this? Current through this will be I. Let's assume this current is IR. So IR will be equals to V, that is 2 kilovolt by R. Now I don't know R again. So remember, this is R dash. This is not R actually. Sorry, this is not R. This is not R. This is R dash, because I have referred the R into the primary. So my power consumed I know is 10 kilowatt in the R. So it will be basically it like power consumed P across the resistor is 10 kilowatt. That is equals to IR square into R. So from here I can remove the variable R, that is R equals to 10 divided by IR square. So from here I can simply find out, I can put this value, right, of R in this equation. So I have IR over here equals to 2 kilovolt divided by 10. This is kilowatt, right? Don't forget, this is kilowatt. So 10 kilowatt divided by IR square. So basically what happens is I will have a IR here that will be equals to 10 kilo upon 2 kilovolt. So basically what am I getting is this will be 5 amperes. Angle 0. Okay, angle 0, because it is a resistor. There is no phase difference between the voltage and the current. Okay, so this we have found out. So now let's calculate the this current, right? This current is also there. Let's assume this current is IZ. So what will be IZ? IZ will be very simple. IZ will be voltage upon impedance. So voltage is 2 kilovolt and impedance is 1 by 3 whole square into uh, basically ZAB. So what is ZAB? ZAB is ZAB they have given me as now remember I have referred this, right? Referred. So this is the referred value actually. So ZAB is 2000 angle 45, right? So we don't need to write anything else. So because this is already taking care of the referred value. So 2000 angle 45. So from here I can directly write that this will be kilo gets cancelled. So this will be 18. 2 also gets cancelled, right? So automatically this will be 18 angle minus 45. Am I doing this correctly? 9 into, okay, sorry, this will be 9 angle minus 45. Okay, anywhere I have done anything wrong, that is what I'm trying to think. Because if this has larger terms, then I1 will be larger. Yes. So everything here, if I convert everything to this side, this will be some R dash value, but the power will not get changed. Power will be constant, 10 kilowatt. So I'm just trying to think what am I doing wrong here. Somewhere I'm doing something wrong. So here the IR comes out with 5 angle 0. That is not possible actually. 5 angle 0 is not possible. What am I doing wrong? So did I do anything wrong here? So this is 10 gets okay. Oh, sorry. This is 10 squared, right? So here I will have a this squared. Sorry for that. So this will be actually 100 10 kilo actually. This will be 10 kilo. I'm sorry. If this is 10 kilo, right? My current here becomes 1 ampere. I'm really sorry for that. That's why we use different methods to cross verify our answers. So I know you guys were screaming there behind the screen. I know you guys are screaming, sir क्या कर रहे हो आप, क्या कर दिया आपने, क्या कर दिया, इतना बेसिक गलती कैसे कर दिया. Okay, so this will be 1 ampere and IL1 is here, so this is 1 ampere. So this actually I hope this will not change. IAB will be 3 amperes only. If I measure here as well, how much current I'm getting, yeah, that is fine. This should get scaled by thrice. Yeah, this is fine. So this will be 3 amperes only. So I made a mistake here. So this value will be actually here this value will be 1 amperes, right? This value will be 1 amperes. So this is wrong. So 3 divided by root 2 plus 1. So this will be 3.121 and squared plus 2.121 whole square under root. So 3.77 and this will be 2.121 divided by 3.121 tan inverse. So angle will be minus 34.2. Okay, apologies from my end, just a bit of mistake. So in the secondary it will be 5 times this. So 3.77 into 5, this will be 18.85. 18.85 and angle will be minus 34.2. Okay, so Here everything is correct only, so this value comes out to be my, so what will be my actual current I? So I will be equals to IR plus IZ, IR plus IZ. So this will be 5 angle 0 plus 9 angle minus 45. So here this will be 9 divided by root 2. So this is 5 plus 6.36, 6.364 minus j 6.364 plus 5, 3.364 minus 3.364. If I just square 6.364, then take 100. Okay, something again is wrong. This is coming out with 13 point something. Okay, why am I making a mistake here? This is 9, 2000 goes away. Okay, 2000 is here. Again I'm making something, some sort of mistake I'm making. Okay. Okay. Okay, actually what is the winding current? So this IL1 is here, that is the winding current. So same current flows through the winding, first of the winding, and other half of the winding some other current flows. Okay, actually right, I made a mistake here, sorry for that. Actually the winding here carries two different currents. Okay, the winding here carries two different currents. So this first portion, this portion, right, is this much of the portion, this much of the turns carries how much current? This much of the portion carries actually is current, no problem. But this much portion of the winding, right, it does not carry is amount of current. It does not carry is amount of current. So how much current does it carry? It carries only IL1 current, right? So whatever current is coming here, it is in series with this portion. So basically what is happening is, if I write down the balance MMF equation, okay, so because there will be a bit of confusion, I know, I want to clear that confusion. So here I was wrong. Secondary current is fine, is current is fine, but is current I have found out, but it is like this is not correct, this is incorrect. So apologies from my end, I made a mistake here. Okay, so basically what is happening, I'm making a lot of mistakes, so maaf kar doge I hope. So now here, right, what we have to do is we have to do the MMF balance equation, MMF balance equation, or otherwise as well, like I will show you directly how you can write without writing the MMF equation. So to write the MMF balance equation, so initially this is an ideal transformer, so let's assume IM current is almost equal to 0. Okay, so the MMF provided by the primary N1 I1 should be balanced out by the MMF on the secondary. So what is the MMF on the secondary? So this, right, this portion of the coil has 600 turns, and what is the current flowing through this portion of the coil? It is IS. It is IS. So the current flowing through this portion of the coil will be 600 into IS. And this portion of the coil, how much current is flowing? So this portion of the coil has a current of IL2, has a current of IL2. So this will be 400 into IL2. This will be balancing out. So here I was wrong actually. So from here we have to write down the phasor equation. All these are phasor quantities. Okay, remember all these are phasor quantities. Phasor quantities. So it's best to actually refer it, otherwise you will mess up. Okay, just like me. Okay, just like me you will mess up. So phasor quantities, remember, these are not simple scalar quantities that I can simply add them. No, I cannot simply add them. So N1 is basically 200. So I1 will be equals to what? 600 divided by 200 into IS. Now what is IS? IS I had just found out is 3.77 angle minus 34.2 degrees then plus 400 divided by 200 into what is the value of IL1. IL1 value is supposed to be 1 angle 0. 1 angle 0. So now this will be what? 3.77 into 3. So it comes out to be 11.31 angle minus 34.2 degrees plus 2 angle 0 degrees. So okay, I have to calculate this value. So 34.3 cos 34.3 cos into 11.31. So this value comes out to be 9.343 plus 11.31 into sine, right? 34.3 sine. Okay, so this is actually minus j 3571. Okay, and plus of course 2 is there, so this will come out to be 9.343 plus 2 11.343 minus j 6.3571. So whole square plus 11.343 whole square whole under root, that is equals to 16. Still this comes out to be 16. What I was getting previously, I have to check that. 16. Okay, what was getting here? Yeah, it was same only, right? I guess, yeah, it was same, the same. Right now I am relieved. Okay, so here, right, 16, and what is the angle will be 6.3751 divided by 11.343. Okay, tan inverse, so this will be minus 29.33. So you can observe that now answers are matching. So of course whatever we have done is correct only. So he same, right, same values, 11.64, 11.43, almost approximately same. 6.35 here also, 6.64, almost approximately. Okay, now no, so this is subtraction, right? No, this is right, sorry, this is just yeah, this is subtraction only. So this will be minus j also will be there, right? Forgot to write the minus j. So this value will be approximately same only, that is 16 angle minus of 29.33 degrees. So this will be the answer of this question basically. Okay, I hope you have understood. Like this kind of question has not been asked yet, but I am expecting a question that it will be asked. So always try to like better will be using the referring of the sources. It simplifies the circuit very much. You don't have to think about all this, right? You don't have to think about this winding coil, all this. Okay, just it takes into account the impedance referring case. Okay, so now let's solve the next question. So this is the next question, and air core radio frequency transformer as shown has a primary and a secondary winding. The mutual inductance is shown here between the windings of the transformer in microhenry. So they are asking me what will be the mutual inductance in this winding. So how do I find out the mutual inductance? So this, right, is a open-ended terminal. So I am measuring 5 volt across this. So let's solve this question. So if I measure the current I1, okay, so all any current I, okay, through this, like this is an IR. So what is the current IR? So this current is 0, right? This is open ended, no current will flow through here, no current will flow through here. So this IR current is going here. Now I have two options, either I will go here or go here. So if I see, this IR current actually has to come from here only. So it is coming from the coil, so IR current will come from here, and same current will flow through here, IR. So ultimately through the ground, right, no current is flowing. current is coming from the transformer only. Okay, so this is the current actually IR. Okay, so now uh, so they are asking me, we are providing a 100-volt kilohertz source and I'm getting 5-volt peak to peak voltage. I'm getting 5-volt peak to peak. Everything is written in terms of peak. So everything, if I calculate any current, that also will be peak to peak. Okay, don't get confused. If I am calculating the current, that current will come out to be peak to peak because voltage is peak to peak. Okay, so here I can directly write what is my IR current. IR current will be 5 divided by 22. Okay, V peak to peak divided by 22, whatever is the peak to peak value. I don't know what is the peak to peak value. Assumption is it is a peak to peak value, so I am not writing anything. Assumption is everything is peak to peak, whatever calculation, current and voltage are peak to peak. Okay, what do I know? So they're telling me that I'm observing a 7.3 volt across the secondary. How can I observe a 7.3 voltage across the secondary? How is it possible? So basically what is happening is that uh, a voltage transformation is happening, right? Voltage transformation. So if I have if actually this, right, this is like a mutual inductor. Okay, so if some current is flowing in the primary of this coil, then some voltage will be induced in the secondary. And what is the equation for the voltage induced in the secondary? V2 will be equals to j omega into I1 into m, j omega m into I1, right? If this, I hope you remember, this is the magnitude of the voltage. This is the voltage actually, and the magnitude of the voltage, magnitude of V2 will be equals to omega m into I1. Okay, so from here I can directly know what is my I1, what is, I need to find out m, and what is my magnitude of V2. They've given me as peak to peak. So current is also in peak to peak, so magnitude of V2 will also be in peak to peak. So from here I can directly write my value of the m will be equals to magnitude of V2, that is 7.3 peak to peak, divided by the current, that is 5 by 22 peak to peak, divided by the omega is what, 2 into pi into f is 100 kilohertz, right? F is 100 kilohertz. Okay, so 10 cube. So now if I calculate the values here, 7.3 into 22, so this will be 160, and this, let me write in micro, right? So this is 10, so basically I have to divide by pi only. Divide by pi. If I divide by pi, value comes out to be 51.6. so I have just converted into micro henry. Okay, I hope this much you can do. So this will be 51.12 micro henry. This will be the answer of this question. Now let's move on to the next question. Next question is just for referring. So whatever we have discussed, right, these things actually get asked. It's not like I'm wasting your time. This is a recent question. It's not like very old question. So these things will be asked. Whatever I'm teaching you, trust me, all this will be asked in the examination. Okay, so let's solve this. For the circuit shown below, source frequency is given, the mutual inductance between the magnetically coupled coil is also given, their self inductance also is given, the Thevenin impedance seen from the source. Very simple. They are asking me to find out the Thevenin impedance seen from the source. So either you can refer this impedance here, or you can directly solve. Both ways work, whichever one is suitable to you. Okay, whichever one is suitable to you, because they have given you the mutual inductance, so we can solve using that basic KVL. So what I can do, right, first of all I will find out the impedance seen from here, Zn dash. Okay, I will try to find out the impedance seen from here, and from there I can find out the overall impedance. Just make this connection. Okay, that you can do, or you can refer this whole thing into the primary, but I will not actually prefer that. I will not prefer that method. Okay, referring this to the primary. Okay, but you can of course refer it to the primary. How can I refer? I will tell you also how can I refer. So here, right, you have to assume few directions of current. Okay, so if this is dot, that means this is plus and this is plus, right? So current will flow like this, and here current will flow like this only, because current will come from the source only. Okay, so we will discuss about this. So we will solve this again using two methods. First one will be the basic method that we already know. So basic method that we already know is, first I will try to calculate impedance from here. What is the impedance from here? So the impedance from here will be, let me choose this in isolation. So I have a transformer here, I have this capacitor here, this is 50 microfarad, this will be basically 125 uh, Henry, right? 125 Henry is there. So like, let me write this as L1, let me write this as L2 for now, and there is a mutual inductance of M. Okay, and of course I1. Okay, so if I write the KVL in the first loop, so basically what I have to find out, I have to find out this, right? If I apply a fictitious voltage source here, V1 I1, so it will be uh, V1 will be equals to, like, this is dot only, so V1 will be equals to I1 j omega, so I can write minus of V1 plus j omega L1 into I1, and mutual inductance is there, and both of them are opposing, because on one of the coil it is entering the dot, other coil it is leaving, so it will oppose, so it will be minus j omega M into I2. Okay, minus j omega M into I2. Now this will be what? This will be in this case here, this will be equals to 0. So from here I can directly calculate V1. uh, let's put it like this only, let's calculate the secondary side. So if I write the KVL in the secondary side, this will be again here plus minus, now the drop is like this, right? So I will write like this, so it will be plus j omega L2 into I2, and again mutual EMF will oppose it, so it will be j omega M into I2 plus 1 by j omega C into, sorry, this will be I1, right? I1 into I2, this will be equals to 0. So from here I can directly write what is my I2 is actually equals to. So my I2 will be equals to j omega M I1 divided by j omega L2 plus, sorry, minus j, I can cancel out, basically j will not be there. Okay, so this will be 1 by omega C. Okay, so from here I can directly write what is my I2. So this I will replace in this equation. So if I replace in this equation, I will get V1 will be equals to j omega L1 into I1 minus j omega is already there, another omega is also here. So okay, omega will not get cancelled, sorry, omega will not get cancelled. So I will multiply omega here, so this will be j omega whole square M square into I1 divided by omega L2 minus 1 by omega C. So my V1 by I1 comes out to be, if I just take common j omega, right, I will take common j omega, this particular value. So I can write this as j omega into, like, this is like inductor, okay, j omega into L equivalent. So this is the reactance, basically this is the amount of reactance. So I will just quickly calculate the values. So omega have the, yes, omega is 5,000 radian per second. So omega is 5,000 radian per second. Okay, so value will be here. I will just quickly calculate this value. So let us calculate. So what is my m? Let me write down the value. So omega is 5,000. What is my m? M is equals to uh, 5 millihenry. M is equals to 5 millihenry. L1 is equals to 125 millihenry. 125 millihenry, and L2 is equals to 1 millihenry. So I can directly write it here that my omega is like this is 5,000 into L1 I1. L1 is, so 125 milli into I1 is anyways gone, okay, minus omega square. So, okay, so not omega, sorry, I have taken common omega, right? So this will be my L equivalent. I just calculating my L equivalent. It will be uh, L1 only. So L1 is 125 milli, sorry, there is alarm, 125 milli uh, minus omega, that is 5,000 into m square. M square will be 5 milli square, basically 5 into 10 raised to power minus 6 divided by omega into L2. So omega into L2 is 1 milli, and I am multiplying 5,000, so it will be 5 only, minus 1 by omega c. So okay, I forgot to write down the value of c as well. So my c will be equals to 50 microfarad. 50 microfarad. Okay, c will be equals to 50 microfarad. So this will be 50 micro into radian, so this will be 50 into 5,000, right? This will be milli, so this will be 10 raised to power minus uh, micro is there, right? 10, so 10 cube will go here basically. So this will be 15 to 20, so this will be 4, so this will be 1. So uh this is milli, this will also be milli only, 25. So 125 minus 25, so L equivalent comes out to be 100 millihenry. Okay, so L equivalent comes out to be 100 millihenry. Now I can replace this whole circuit. Okay, what is the whole circuit? So whole circuit is, I have a resistor here of 4 ohms. I have another resistor here of 4 ohms. I have another resistor here of 2 ohms, right? And I have a, like, from here I can see a L equivalent of 100 millihenry. L equivalent of 100 millihenry. Hundred millihenry. Okay, so from now you can simply find out the Z input impedance, right? So input impedance will be what? Input impedance will be very simple now. Input impedance, this will be like what is the j omega L equivalent? J omega L equivalent will be 5,000 into 100 milli, so it will be 5 kilo radian. So this will be 500 ohms, right? Am I correct? I'm getting J 500 ohms. Okay, so let's basically calculate this values. So it will be 2 plus J 500 into 4 divided by 6 plus J 500 plus 4. Correct? Am I correct? So this will be the value basically. So they are asking the impedance, right? Yeah, ZTH. They are asking just the ZTH. So yeah, if I just calculate this ZTH, this value here will come out to be like yeah, sorry, one very small mistake I had made here. Actually this was omega square, right? I know again you guys are screaming. So here, right, okay, no, omega square was not there. Actually this omega was taken in common, right? So if this omega was taken in common, so this will be L1 only, that is 125 milli. Okay, this will be omega only, this will be 5 only, m square will be there. Okay, m square is okay, this will be, sorry, this will be m square, right? Sorry. So here I will have 25. Okay, I missed the square, so I'm making this kind of mistake. So this will be 25. So 5 into 25 is 125 only. So actually the interesting fact about this transformer is L equivalent is 0. L equivalent is 0, so the circuit, right, can be replaced with L equivalent, that is 0. If L equivalent is 0, it is like a short circuit. In frequency domain it is like a short circuit. Okay, in frequency domain it is like a short circuit. That's it. So now it becomes very easy to calculate the impedance. So it is basically very easy, right? L equivalent is 0, that's why the j omega into L equivalent, j omega into L equivalent will be 0. So I can write 4 plus 2 into 4 divided by 6. So this will be equals to 4 divided by 3, right? So 4 divided by 3, 1.33. So this will be 5.33 ohms. Okay, that's how simple this question was actually. But finding the L equivalent is very tedious. Okay, remember, every other, wherever you will go, you will see that they have converted this, right, to a T model. They converted this to a T model. I don't want you to remember the T model. Okay, I want you to solve with the basics. So anywhere, right, whatever we have learned, we have used those concepts. We have not converted it into T model. You will go anywhere else, they will convert this particular circuit into T model and then they will solve. Okay, I don't want you to mug up, right, mug up the circuits, okay, without understanding what is happening in the coils. Okay, we have learned everything internally, what is actually happening in the transformer, trust me. Okay, you will go, you will find the PYQ solutions there, they will not solve it like this. Okay, this is another question, so this lecture is going long. So we have to find out the resonant frequency of the circuit if the coefficient of coupling is 0. So here the coefficient of coupling is 0, k is 0, that means there is no mutual inductance. So m is 0. Sorry, coefficient of coupling is non-zero. Okay, if coefficient coupling is 0, will resonant frequency be same if coefficient coupling is non-zero? So okay, first let us find out the resonant frequency with the coefficient of coupling being 0, then we will discuss with the coefficient of coupling being non-zero. Okay, so first case 1, if k coefficient of coupling is 0, if k is 0, that means what is my m? M is k into under root L1 L2. So k is 0, so under, I don't care whatever is the under root L1 L2 value, so this will come out to be simply 0 Henry. Okay, so this is 0 Henry. So now I can easily find out the Z equivalent, like I have to find out the Z equivalent, then only in resonance what happens? In resonance basically what we do, in resonance basically we make the imaginary, like this will be my input impedance seen from the transformer. Okay, this will be my input impedance seen from here, right, input impedance, and we make the imaginary portion to be equal to 0. So for that, right, I have to find out the impedance seen from these 2 points. For that, this 1 ohm is connected here, I have to refer to this to the primary. Correct, I have to refer this 1 ohm to the primary. Okay, so what will be the referred value here? Referred value will be simple, very easy, right? It will be a resistor only. It will be a resistor or inductor also. Okay, there is no mutual inductance. So if there is no mutual inductance, right, basically this circuit is totally detached, right? Zn will just be the self inductance. We will see, I will show you. It will be just this self inductance, that is 2 Henry. I will show you. If m is 0, okay, then let's write down the KVLs. Same thing, same procedure we will follow. So if I apply some input voltage here, V in dash, there will be some current here, I in, this current is I in dash, okay, I in dash into like j omega 2, that is j omega 2, and again assumption is one current is entering, other current is leaving, so the mutual voltage due to the mutual inductance will be in the opposite sign. But remember, m is 0, mutual inductance is 0, so m is 0, so 0 into any finite number, whatever the number is, I don't care, okay, it will be I2, it is 0 only. So basically my V in dash upon I in dash is coming out to be j omega L only, L1, this is L1, right, inductance of the primary, j omega L1 only, so this will be j omega I will obviously find out what is, okay, omega we have to find out, right? So it is j omega L1, so it is basically j omega L equivalent. So from here I can directly write what is my L equivalent. So what is my L equivalent? L equivalent is L1 only, that is 2 Henry. Now I can redraw the circuit, okay, I can draw the circuit, whatever circuit they have given me, basically, right? When the coefficient of coupling is 0, then this will be 2 Henry only. So what will be the resonance frequency? Simply, what is the input impedance seen from the supply? It will be j omega L plus 1 by j omega C. Okay, so Zin, like I have to make it 0, right? For resonance condition I have to make Zin to be equal to 0. If it goes to 0, then current will be infinity, but we are not discussing about that right now. We have to make the imaginary 0. So what we can do, like if we want to improve this circuit, right, what you can do is, instead of making this non-ideal case, let's keep a resistor, because I know you guys will go mad and I don't want you to go mad. Okay, let's keep the 1 ohm here, and yeah, now you will not go mad. Okay, now we'll say now the circuit is fine, there will be a finite current, so this will be 1 ohms here. Okay, so this will be R plus j omega. So here, right, R is 1 ohm, so it does not matter. So the my imaginary has to be 0. So basically my omega square will be 1 by LC. So omega will be equals to 1 by under root LC. So it will be 1 radian per second. When the coefficient of coupling is 0, when it is non-zero, so if K is non-zero, right, if K is non-zero, then will the resonant frequency change? 101% it will change. Will it change? It will not change actually, because I have a resistor connected, or no, it will actually change, sorry, it will change. So if K is non-zero, what will happen? Let's assume that, okay, I have not discussed if the coefficient coupling is non-zero. If the coefficient coupling, what will be the resonant, will the resonant frequency be same? And I should have written here, calculate the resonant frequency for coefficient of coupling equals to 1. Okay, so equals to 1. So when it is equals to 1, basically, again, what will be my L equivalent, right? I want to find out the L equivalent here, basically. So here again the same method, V1, this V1 I am applying, okay, I1 is flowing here, I2 is flowing here. Okay, now it is like bread and butter for you, right? It is bread and butter. So current incoming and outgoing. So basically what I will write, so V1 minus of V1 plus I1 into J omega into 2, and mutual inductance is there, that will be due to the current I2 into j omega into m. What is m this time? So m will be k into under root L1 L2, so it will be under root 2 basically. Okay, this will be equals to 0. So yeah, so my V1 is equals to I1 minus I2 into, this is under root 2 and this is 2, and of course j omega is there. j omega is there. Okay, so uh, my okay, why is this alarm always coming out? Okay, so in the secondary I can write here the drop will be like this, right? This will be plus, this will be minus, because like it is like acting as a load. So this will be uh, plus j omega L2. L2 is 1 and minus into I2 is there obviously, minus the mutual inductance j omega m, m is under root 2 into I1, and of course plus I2 is there. It will be a bit difficult, okay, it will be a bit difficult because complex calculations will be there. It will not be just like L equivalent here, right? It will be Z equivalent. Sorry, this will not be L equivalent, it will be Z equivalent. Okay, so I2 into 1, yes, it is correct, equals to 0. So from here I can directly write what is my I2 current. So I2 current will be j omega root 2 divided by j omega uh, plus 1. Okay, so yeah, this is my I2 current into I1, of course. So I will replace this I2 I'll replace this I2 in the primary. So I2 is this value. So yeah, I2 I can put here actually, right? I can put here. So this will be V1 equals to this 2I1 minus this will be I2 into 2 is there, right? I2 into root 2 is there. So this will become actually j omega 2 divided by j omega plus 1 into j omega is already there in the outside. Okay, we will add that later. We will add that later. Multiply that later. So this will not be I2 actually, this will be I1 now, because I've converted this into I1. I1 j omega root 2, yeah, j omega plus 1. Now I can take the I1 as well outside. So this will be V1 by I1. This will be j 2 omega plus 2 and minus j 2 omega. Actually this is not that complex that I thought. So this will be j omega plus 1 into j omega. So ultimately what I am getting is here j2 omega is simply getting cancelled. So if j2 omega are simply getting cancelled, this will be 2 divided by j omega plus 1. Okay, and this if I rationalize, this will be 2 into 1 minus j omega divided by 1 plus omega whole square. Okay, something is wrong. What is wrong I will tell you. This is minus, okay, minus is here, this will be 2, okay, 2 is there, okay, this will be minus j2 omega only, yes, this is correct. Okay, we are stuck. Okay, what is the problem? I will tell you what is the problem. The problem is, right, resonance frequency will not exist because I designed this question. Resonance frequency will not actually exist. So what is happening is V1 by I1 is this value. Okay, so if V1 by I1 is this value, I have an impedance here that has a impedance like this, 1 minus j omega divided by 1 plus omega square, and here I have an impedance that is 1 by j omega c, correct? This was capacitive, if you remember, this was capacitive, right, on secondary. So basically I have to make the imaginary portion 0, right? Here I have a resistor as well, some r. So here, right, because I designed the question, it went wrong, but what happened, I have to make the imaginary portion of the impedance 0. How will you make the imaginary 0? So this should have been plus j omega and this should have been, this is already minus j omega, right? So automatically then they will cancel out. So actually for no value of omega this is possible. For no valid value of omega, possible. I cannot make the imaginary term 0, 0. Why? Because this is providing negative sign. This is also providing negative sign, right? If I take this j on the numerator, this will be minus j by omega c. So there is a problem. There is a problem, right? Like both are negative sign. I cannot simply cancel them out. So one has to oppose the other one, right? One has to be the positive sign, other one has to be the negative sign. So here we cannot actually cancel them out. So there is no valid value of omega. Only omega will exist for the first case. Okay, just be careful regarding that. So yeah, this is the last question that we will do in today's lecture basically. So here we have an audio transformer is used to match a 100 ohm resistive load to an electronic source. Okay, so we are discussing about impedance match. So they're telling me I have an audio transformer. Okay, I have an audio transformer, and the audio transformer is used to match a 100 ohm resistive load. It is used to match a 100 ohm resistive load. That means the referred impedance I should be able to get is 100 ohms. Okay, no, not referred impedance. It is used to match a 100 ohm resistive load. So on the other side of the transformer I will have a resistance that is 100 ohms that I will use for impedance matching. Okay, what they're telling me, which can be modeled as a constant 6 volt source in series with an internal resistance of 4000 ohms. So this whole thing, this whole source can be modeled with a voltage source of 6 volts, 6 volts, and it can be modeled with an impedance of 4000 ohms. Okay, so what they're telling me, that the audio frequency, an audio frequency transformer is used to match a resistor, match a 100 ohm resistive load to an electronic source, which can be modeled as a constant 6 volt source in series impedance. So I have a source here and I have to match the impedance. Basically matching the impedance means I have to match the source impedance, right? I have to match the source impedance. So basically why do we match the source impedance? I will tell you. So you have learned about maximum power transfer theorem. So in maximum power transfer theorem, if I connect a load here ZL, I want the maximum power to go to this load, right? I need to match the impedance, that is ZL should be equals to ZS conjugate, but in our case it is real, so it will be simply ZS 4000 only. So I have to match the impedance, but currently I have 100 ohms only. So how will I match the impedance? So what you will do is, this source will be there 4000 ohms, that is fine. This will 6 volt source will be there. Okay, and this will be dot dot, and I have to match the impedance basically, and I have a 100 ohm impedance here. So from here, right, I need actually 4000 ohms. So what are they asking? They are asking me the required turns ratio for maximum power transfer by matching the source and load impedance. So what will be the source, what will be the turns ratio? So I know if I refer this to the on the left hand side, so it will be 100 into the, let's assume this as n1 n2. So this will be n1 divided by n2 whole square into 100. So into 100 is already there. This should be equals to 4000 because I want to do the impedance matching. So this will be equals to 40. So n1 by n2 whole square is 40, or if I take the under root, right, actually we should have picked up better numbers. Under root of this will be roughly 6.32. This will be roughly 6.32. So of course n1 by n2 cannot be a fraction, or it can be a fraction as well. Okay, it can be a fraction as well, there is no problem. Yeah, it can be a fraction as well. So yeah, n1 by n2 will be 6.32. so this is the first answer, turns ratio. What about the second answer? The resulting current, voltage and power at the load under these conditions. So in maximum power transfer, very simple, right? So simply I can replace this whole circuit equivalent. 6 volt, 4000 impedance, 4000 ohm impedance. This will be basically 4000 ohms only. So it's very simple, right? It's very simple. Like what will be the current will be like RMS value. If this is a 6 volt source, RMS value of the current will be 6 divided by 8000. Okay, that is equals to 6 by 8 in milliamperes. So it is 0.75 milliamperes. Voltage is very simple, right? Voltage will be just half, it will be 3 volts. And power consumed where? At the load, power consumed at the load. So power at the load will be V into I, or like you can directly write it will be IRMS whole square into R. So it will be 0.75 whole square into R. R is 4000. Remember this is milliamperes, right? Milliamperes. This is milliamperes. So okay. Can to minus 6 also there. So this will be 0.75 whole square into 4, that is 2.25 milliwatts. This will be the power loss, power consumed in the load. Okay, so yeah, I hope you have enjoyed this lecture. We learned a lot of new things, and trust me, whatever we learned with basic. I've not told you any circuits to remember. Trust me, those T model every other educator will tell you to remember, but we have not gone to that path where we have solved fundamentally. This will be helpful immensely during your examination. So if you enjoyed this lecture, make sure to comment down below whatever you felt regarding the concepts. You can comment down below. Make sure to like the video, and I will see you in the next lecture with practical transformers. So thank you for watching, and I will see you in the next lecture. Until then, happy learning.